Hi everyone, my name is Steve. Today we're going to talk about another sorting algorithm called Heap Sort. It's a very famous algorithm. It combines the better attributes of both insertion sort and merge sort, which are two sorting algorithms that we just talked about in the previous weeks. So if you missed that, I'll put links down below in the description box. Feel free to check it out to review. The running time of Heap Sort is nlogn, which is very ideal. And Heap Sort is similar to insertion sort, but unlike merge sort in the context that Heap Sort doesn't use any extra space. It's using constant O1 extra space, while merge sort uses extra memory. That's what I mean by Heap Sort combines the better attributes of both insertion sort and merge sort. With that said, let's dive into more details about Heap Sort. Alright, first let's talk about what is a heap. This is a data structure. A heap, it has to be a balanced binary tree. What that means is either the lowest level or the level above the lowest level must all have leaves. A leaf is at the bottom layer. It doesn't have any other children. That's what a leaf means by definition. Or in other words, the tree is completely filled on all levels except possibly the lowest, which is filled from the left up to a certain point. Or in the most simple terms, what it means is a nearly complete binary tree. It's almost complete. It could be a completely full binary tree. That's also a valid heap, but in other cases, it's nearly completely full. Let's take a look at this randomly ordered array. Here are the indices of this array elements. How we're going to map this into a valid heap, we can simply put the first one is going to be the root of the heap. Again, a heap is a binary tree, so the first one is just going to be the root of the binary tree, and following the rest, everything on the right of this first element, we'll just put them as the children of this root node from left to the right. Okay, so 14 is the left child, 10 is the right child. And at this moment, we can take a look. So how do we map the relationships between the parents and the children? So we need some indices to help us to do so. What we need is these three formulas. Given a child index, we can use this, the first formula, to compute its parent index. For example, the child index is 2. So 2 divided by 2 is 1. That means the parent index of this one is 1, which is correct, right? And then also given a parent index, we can use the last two formulas to compute its two children's indices. For example, the parent index is 1. So 1 times 2 is 2. That's why the left child of 1 is 2, indexed as 2. And again, 2 times 1 plus 1 is 3. That's why the right child of this one is 3, indexed at 3. These are the three formulas that we're going to need to manipulate the elements based on the indices of the elements inside this array. And on most computers, this could be easily achieved by shifting the binary representation of I to the left. This is how we can achieve this by shifting binary representation of I to the left by 1 bit position to get the left child. And we can do the same to shift the binary representation of I to the left by 1 position and plus 1. That's going to give us the right child. And similarly, we can shift the binary representation of the child index to the right by 1 position to get its parent index. On most computers, we can do that, which makes things very efficient. All right, with that said, we'll continue to map the remainder of this array into a valid heap structure. So 8, continue, 7, 9, 3, 2, 4, and 1. So we keep mapping things from the left towards the right. That's how we can map any randomly ordered array into a valid heap data structure. With that said, we can talk about there are two types of heaps. One is called max-heap. What that means is for every node I other than the root, the parent of node I is always greater than or equal to this node itself. In other words, the value of a node is at most the value of its parent. It couldn't be bigger. That's what it means. Which indicates the largest element in the max heap is at the root level. Min heap, very simple, a different type of heap. The reason it's called min heap is because it's the opposite of max heap, which means for every node I other than the root node, its parent is going to be guaranteed smaller than or equal to I. The value of a node is at least the value of its parent. That's what it means. That means the smallest element in the min heap is sitting at the root. Now let's talk about what's the definition of the height of a binary tree or a heap. We define the height to be the number of edges on the longest simple downward path from the node to a leaf. Remember, a node to a leaf. For example, if we take the node with value 7, this one has a height of 1. That is because there is only one edge between this one to its next leaf. That's why this node with value 7 has a height of 1. So now we define the height of a heap. That is, the height of its root is going to be the height of the heap. So looking at this heap, the height of this heap is 3, because from the root all the way to the leaf, there are 3 edges, 1, 2, 3, or 1, 2, 3, or 1, 2, 3, right? 3 edges. So the height of this heap is 3. Why are we talking about this? Let's see. Now we know the number of edges in the longest path for this given example is 3. Let's think about the minimum and maximum number of nodes in a heap. So the minimum number of nodes in a heap is going to be 2 to the power of h. H in this case is 3. So the minimum number of nodes is going to be 2 to the power of 3, which is 8. So it's going to be a tree like this. 1, 2, 3, 4, 5, 6, 7, 8. There's a total of 8 nodes in this heap. This is a heap that has the minimum number of nodes in order to make it a valid heap. We couldn't have one less node in this heap, given the height of the heap is 3. Now let's think about the maximum number of nodes in the heap. Apparently, it's going to be, we can make this one a completely full binary tree. That's going to be the maximum number of nodes in the heap that's possibly allowed with a height of 3, right? So that's going to be looking like this. A total number of nodes in this example is going to be 15. How can we map 15 to the height of the binary tree? That's going to be 2 to the power of h plus 1. The result of that is going to minus 1. That's going to give us 15. So 3 here, 3 plus 1 is 4. 2 to the power of 4 is 16. 16 minus 1 is 15. So that's going to be giving us a tree like this. Again, why are we talking about this? Let's see. We need to know the number of nodes of n. Suppose n means the number of total nodes in this given binary tree or this heap. So now we know n is within this range. It is greater than or equal to 2 to the power of h, or smaller than or equal to 2 to the power of h plus 1 minus 1. This is the range of this number of nodes. How we can simplify this? We can simplify this to be like this. We simply strip off this minus 1 and remove this equal sign. That means we have added 1 to this, which means it's going to be guaranteed exactly greater than n. And how can we even simplify this or convert this to something more meaningful? We can apply logarithm function to all 3 parts of this formula. That's going to give us this. So we strip off 2 and we put logarithm function to this middle part, and then we can take off this 2 here as well. And what this means in big O notation or in algorithm analysis, it's going to give us in theta notation. It could be written as height is in theta notation of log n. N is the number of nodes in the binary tree. That is why the basic operations on heaps run in time at most proportional to the height of the tree. Therefore, it is log n time. With that said, let's talk about one very important procedure call. We call it max-heapify or heapify. This is a call to maintain the max-heap property. A max-heapify assumes the subtrees rooted at the left side and the right side, they are both max heaps already, which means they satisfy the max-heap properties. Only that the AI, the node that we are traversing right now, might be smaller than its children, either its left or right child. Thus, it's violating the max-heap property. So what we need to do is this max-heap function is going to let the value at AI float down gradually in the max-heap so that the subtree will still obey the max-heap property. Let's take a look at this simple binary tree on the left side. Is this a valid heap, max-heap? No, apparently it's not. Looking at this node with value 2, this one is smaller than both of its left and right children, so this is not a valid max heap, right? So what we will do is we'll move this one down, float this one gradually down, right? Assuming both of its left and right subtrees are both valid max heaps, which is true in this case, right? This subtree starting with the root of node of value 14 is a valid max heap, and this one is a valid max heap as well. So we'll call max-heapify on this node. So this one is going to be switched down, gradually moved down. Now this one is a valid max heap, But how about this subtree? No, it is not. So we'll continue to call this max-heapify. 2 is going to be switched with 8. Now this part is a valid max heap, so that this entire part is also a valid max heap. And the time complexity of calling this max-heapify is OH, which is the height of the heap. As you can see, it takes O1 time, basically constant time, to fix up the relationship between the elements, the root node and its left and right children. In the worst case, we'll have to perform this operation at every level of this subtree. As you can see, we performed this O1 constant time operation at this level, right? So this max-heapify operation yields OH time complexity. This is O log n, where n is the number of elements in this entire tree. Now let's take a look at this example that we looked in the very beginning of this video. We're given this randomly ordered array. The second half of this array, all of them, they are what? Mapped into this heap. In this visual representation, we see all of the last half, the second half of the array, they are all leaves in the heap, right? So how can we implement this build max heap procedure call? Easy. What we can do is we can just go from the last one of the first half, which is 7, all the way to the first one. We'll call max-heapify. That's going to give us, so we call 7, now 8. We keep decrementing I, then 10, then 14, then 16. We go all the way to the first element of the given index. After we call max-heapify for the first half of the given array, then we have built a max heap. If that's kind of abstract, let's just build a max heap from an unordered array from scratch. Suppose we're given this random array. This is the index of this array. How can we build a max heap from this? First, we'll put everything into the heap representation. So this is how we put an array into a heap. This is not a max heap yet. This is just a heap. We are using a heap representation to represent this array. How we did that is, remember, this is the indices 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 from left to right. This is how we constructed this binary tree. Remember, this is not a valid max heap yet. Now, what we will do is we will, from the last element of the first half of this array, we will call max-heapify. That means we'll start from this one, 16, right? Which is the last element of the first half. The first half is 1, 2, 3, 4, 5. These 5 elements, this is the first half of the given input, as we saw in the previous slide. So the first one we're going to call the max-heapify procedure call is 16. How do we max-heapify 16? We compare with its left and right children. It doesn't have a right child, so we'll compare with its left child. It's actually greater than its left child, so we don't need to do anything. We move on. We move on to this one. I is decrementing always. We move on to this one. This one has a value of 2. 2 is actually smaller than both of its left and right children. What we're going to do is we'll swap it up with 14. Now, this one is a valid max heap, this subtree, right? So we'll continue to decrement I in this case. So I becomes at index 3. That is this one. Is this one a valid max heap for this subtree? No, it's not. We're going to swap it up with 10. 10 is going to be swapped to this root position. I is going to be 2. 2 is here. So we'll see, is this a valid max heap? Apparently it's not. It's smaller than both of its left and right children. So what we will do is we'll swap it up with 16. 16 is going down. Now we'll continue to call max-heapify on this one because this one is not greater than its children, right? Its left child is not. So we'll swap it up also. Now we'll keep decrementing I until the first element, which is 1. In this case, this is 4. Is 4 a valid position? No, it's not. We need to swap it. So 4 is going to be switched with 16. Is this one a valid heap? No, it's still not. So we'll swap it down. Is this one a valid one? No, it's not. Continue to swap it. At this point, this is a valid max heap. So we have finished building a valid max heap from a randomly ordered array by following these two simple lines of pseudocode. What this means again is we start from the last element of the first half of the given input array. We go all the way down until the first element. Along the way, we call max-heapify on every single element of the first half. That's how we achieved it. The time complexity of this build max heap is going to be on. It's not actually nlogn. The main reason is this build max heap algorithm, the actual heapify cost is not nlogn for all elements. When this max-heapify is called, the running time depends on how far an element might move down in the tree before the process terminates. In other words, it totally depends on the height of the element in the heap. In the worst case, the element might go down all the way to the leaf level. The detailed mathematical analysis is beyond the scope of this video, but for us right now, let's just keep in mind the time complexity of building a max heap or just building a valid heap is going to be on. Now let's talk about Heapsort, the meat of this program. All of the time that we spent up to now is to help us prepare for the introduction of Heapsort. Now let's get to it. Again, suppose we are given this randomly ordered array. How can we use Heapsort to sort this array into the correct ascending order? Let's take a look at the pseudocode of this Heapsort. We'll look at the pseudocode first, and then we'll write everything into real Java code to help people better understand how we can implement this in real code. So the first step is that we're going to call build max heap. This is the function that we just went through. So I'll just put the max heap, a valid max heap here, and this is the array after we have built this valid max heap. Is going to be switched like this. If you don't recall, just go back a few minutes and revisit it. So what we're going to do is that we're going to start from the last element of this array here or here. The first step, what we're going to do is that we're going to swap it with the root of this max heap, which is going to be what? The guaranteed max of the current valid heap, right? And then we'll strip this off of this heap, put this into the correct position of this array. That's why we decrement the size of the heap, which means we strip this one off and put the current max value to this position. At that point, this one is going to be at the root position. Remember, we called swap. At that point, this one, the remaining tree, is not a valid heap anymore because this one is 1. It's almost guaranteed that it's smaller than its left and right children. What are we going to do? We're going to call max-heapify on this position, on the root node. So we call max-heapify on the position with the index of 1. So we'll continue to call this until there's only one element in the heap. Then that one is guaranteed to be the smallest of all of the elements in the given array. Then we're done. Heapsort is finished. If that's kind of abstract, now let's just walk through how this process is really working. The first step is that we have built this max heap already. This is the max heap that we have built after calling this one line of pseudocode. So now this part of the walkthrough is going to be focusing on the for loop inside this for loop. So start from I equals to 10. So we do a swap with what? With the root node, right? A1 is the index of 1, which is the root node. Now we decrement the size of the heap by 1. That means we just cut off this edge of this heap in our visual representation. So we put this one into the correct position of the final sorted array. And then what we're going to do, apparently we swapped 1 to this position, and this violates the max heap property. So we're going to call max-heapify on this element, call max-heapify. We swap 1 with 14, and then this one is still violating max heap property. So we call max-heapify on that. Keep calling max-heapify on this one. It goes down here. Now the remaining of this tree is still a valid max heap. So at this point, we decrement I by 1. All right. Now I is 9. So we'll continue to follow the instructions of this for loop. We'll swap. Now swap 14 with 1. Swap. Next, we'll decrement the size of the heap by cutting off the edge in the visual representation. So now 14 is put into the correct position, right? Now 1 is still violating the max heap property. It's again at the root of this entire tree. So we'll continue to call max-heapify on root node. So 1 is going to be swapped with 10, and then we'll continue to call max-heapify on this one. This one is going to be swapped with 9. All right. Now this is good. We'll continue to decrement I again. Boom, I is 8. Swap with root node 2 and 10. They are swapped. Continue to call. Then we decrement the size of the heap. All right. Now 10 is put into the correct position. Then we have to call max-heapify on the root node, which is 2. Max-heapify. Swap with 9. Is this a valid max heap for this subtree? No, it's not. Max-heapify on 2. 2 and 3 are swapped. At this point, we're done here. We'll continue to decrement I. I is 7 now. 7. All right, swap. Swap 2 and 9. Now we have to decrement the size of the heap by 1 by cutting off the edge in the visual representation again. So 9 is put into the correct position. Now we call max-heapify of 2. 2 is swapped with 8, should be swapped with 7. Now we continue to swap. The remainder of the binary tree is still a valid heap, so we'll continue to decrement I by 1. What are we going to do? Swap with the root node, which is 8. Now we swapped. Next is we decrement the size of the heap by cutting off the edge in the visual representation and put 8 into the correct position. Now we call max-heapify of 1. This is the root node, which is violating the max-heap property, right? Next, swap with 7. This is still violating, so we swap with 4. All right, this is good. So we continue to decrement I to be 5. Now we swap 2 and 7. 2 and 7 need to be swapped. 7 and 2. We decrement the size of the heap by 1. So by cutting off the edge here and putting 7 into the correct position. Now we'll call max-heapify again here on 2. 2 is smaller than both of its left and right children. So we have to call max-heapify. Now 2 and 4 are swapped. The remainder of the tree is invalid max heap. So we stop. Now continue to decrement I. I is 4. 4, we have to swap with 1. All right, now we swapped. Now we decrement the size of the heap by cutting off the edge now and put 4 into the correct position. Now we call max-heapify on 1. 1 needs to be swapped with 3. Now this is a valid max heap. We're good. Now we continue to decrement I is going to be 3. Now I is 3. 3 swap with 1. These two swap. Now decrement the size of the heap by cutting off the edge and putting 3 into the correct position. Now there are only 2 elements in the binary tree, and this is not a valid heap, so we need to call max-heapify. Swap these two. Continue to decrement I. I is going to be 2, so 2 is going to be swapped with 1. Now it's swapped. We decrement the size of the heap by cutting off the edge and putting 2 into the correct position. Now we call max-heapify. There is only 1 element. Then we're done. At this moment, we break out of this for loop. Remember, I needs to be exactly greater than 1, which means the last element that we're going to execute is going to be 2. Now we put 1 into the final correct position. Now we can see this is the correct order from the originally randomly ordered array input. Now this is correctly ordered ascending order. 1, 2, 3, 4, 7, 8, 9, 10, 14, 16. All right. Now let's talk about the time complexity. What's the time complexity of heap sort? This is the heap sort. This is the pseudocode of heap sort. So let's analyze this line by line. Build max heap. What's the time complexity of this? Remember we talked about that. It's going to be O(n). Now we have a for loop. This for loop is going to run n times, or to be precise, it's going to be run n minus 1. So in big O notation, it's going to be O(n), right? So we put it as O(n). Swap is just a very simple constant operation. So it's going to be O1. And heap size decrement, this is also going to be a constant time. Now, max-heapify, if you recall this is totally proportional to the height of the tree, which is to the logarithm of the number of nodes. That's going to be O log n, right? And then this is going to give us the entire time complexity of the heap sort is going to be what? It's going to be O(n) times log n. Why is this? There's a for loop here. It's going to be this O(n) times O log n, because every single element minus 1 element is going to be needed to consume O log n time. That's why this entire time complexity of heap sort is going to be O(n) log n. All right, with the time complexity explained and we walked through the pseudocode, now let's put the theory, the pseudocode, into the actual real code and see how that really puts into practice. Let's see. So I have created this class and I have created a function called heap sort. So this heap sort, if you recall the pseudocode, the first step that we're going to do is called build max heap. So we're just to implement this function called build max heap. Let's put this logic in place first. This is the first step. Next step after that, what we did is that we went from the last element of this valid max heap all the way up to the second element of this input array, right? What we did is that we first do a swap. So let me first get the heap size. I'll call it heap size. It's going to be array length minus 1. It's going to be the length of the array minus 1. And then we'll have a for loop starting from heap size all the way down to the second element, which is why I needs to be greater than 0. And then I minus minus. We go all the way down. So the first step in the for loop, what we did is that we swapped the last element in the valid max heap with the root node. So what we will do is we'll swap this I with 0 with the position in the root node. So that's the first step. Next step, don't worry about the compilation error. I'm going to implement all of these methods in just a few seconds. Let me put the main logic into place first. Next, what we did is that we decrement the size of the heap by 1, which means we cut off the edge. So let's decrement the size of the heap by 1. So then we have the element to be put in the correct position by cutting off the edge to the last node in the valid max heap. The third step, or the last step of this for loop, is we call max-heapify. So let me write this function called max-heapify. So a few parameters that we're going to take in. First is the array. The second is going to be the parent index, which in this case is going to be 0, which is the root node. That's the index to begin with. And then the second parameter that we need is going to be the size of the heap, which means the upper boundary in terms of the array representation that we can reach. So we'll put heap size here. You'll see why in just a few short seconds. In the end, we can simply just return the original array, which is going to be guaranteed that this output is sorted in ascending order. Now, let's implement these three functions. This one is pretty simple. Let me just create this heap sort I and j. In C++, there's a swap function built in, but in Java, we have to implement this. Very simple, 3 lines. Array I. This is basically to help us swap the two elements indexed as I and j to swap values. Then we can safely override this one with the value at index j, and then we assign this temp value to the value at position j. That's swap function. Now let's implement build max heap. This build max heap is what we just went through. We given a randomly ordered array how we can build a max heap in our visual representation. But in reality, in the actual code, in the logic, it's still operating, manipulating on the simple 1D array. All right, let's see. So what we did is we just went from, if you recall, we start from the last element of the first half. We go all the way to the first element. So we'll start from half minus 1 all the way down to the first element. That's why we have I is greater than or equal to 0, because we need the first element. So this is cutting the length of the array by half. So suppose the length, in our example, the length of the array is 10. So 10 divided by 2 is 5. 5 minus 1 is 4. And in actual code, all array indices start from 0. So the first 5 elements is going to be indexed from 0 all the way up to 4. So the last element of the first half is 4. So we start from 4 all the way down to 0. That's what it means. Now, inside this, what do? We call this function max. All right, let me just put it here. We call max-heapify. So max-heapify, we're taking these parameters array. So the first element is going to be I, and the second element is going to be the size of the heap, which in this case is going to be this entire array length. Length minus 1. So I put it this way. You can put it either without -1 or with -1. It doesn't matter as long as you implement max-heapify properly. So now let's implement max-heapify. What the first parameter really means is the parent index. To make it more descriptive and more meaningful, call it parent index, because if you recall in our slides that we just went through, when we call max-heapify, all of the elements in the second half of the original given input, they are all leaves, right? That means we're always running max-heapify on parents only. If this node doesn't have any children, there's no point to run max-heapify. We're actually building a max heap by running max-heapify on the parents. Next, what does the second parameter represent? The second parameter represents the size of the heap. So in this case, we'll just call it index limit, which means if you go beyond the index limit, those are not part of the valid remainder part of this valid heap that we are iterating on already. They have already been cut off. So that's what it means. Now, inside this max heap, what do? We try to compare with its left and right children. So this is where the three formulas that we just went through comes in very handy, which means how can we get the child indices from the parent index? We need to get both left and right children. So we'll just call it left child index. In this case, which is going to be parent index times 2 plus 1. Remember, in the actual code, all array indices start from 0. So here, left child is going to be plus 1, and let me just copy this, and the right child index is going to be parent index times 2 plus 2. This is the actual representation in actual code. So what we would like to do in this function, in this max-heapify function, is to check whether this subtree is a valid max heap by checking if the node with the value at the root is actually greater than both of its left and right children, right? So we'll just call a max index. In the beginning, we'll just assume parent index is bigger than both of its left and right children. Then we'll check left first. If left child index is smaller than or equal to index limit, and which means it's within the valid boundary of this heap, of the size of the heap. And if array left child index is, if it's greater than array parent, if it's greater than this, which means the left child is greater than the parent, that means the max index should be left child index, right? We can check the right child. So if right child index is smaller than or equal to index limit, again, we need to check if it's within the valid heap size, the valid heap boundary first. And then if array right child index is greater than array, in this case we'll just call max index, because it could have been changed because by this one it could have gone through this. If that is the case, we'll just use the max index to compare. If the right side index is greater than the max index, the value pointed by the max index, then we're just going to assign the right child index to be the max index. At this point, max index could have been updated by this branch or by this branch. So what we want to check is if max index is not equal to parent index. What that means is that, okay, this is not a valid max heap because either the left or the right child of this current root node is greater than the root node. So what we need to do is that we need to swap. We need to swap this, the value at max index, with the value at parent index. This is what we need to do. And after this swap, the node at index max index is not guaranteed to be still a valid max heap. So at this point, what we need to do is to call max-heapify array max index and index limit. This is what we need to call. So this is a recursive function. This one is calling itself at this point until it reaches the case when what? When this one equals to this, then we're done, right? All right, this is the entire function. Now let me hit run and see how it's going to work. Alright, no compilation errors. Now the result seems to be valid. I hope this makes sense, and I'll put the code into my GitHub, and I'll put a link to my GitHub repo down in the description box below. So I highly encourage you guys to check it out and play around with the actual code and set breakpoints in this code so that you can really understand how Heapsort really works behind the scenes. Okay, with all of that said, let's just quickly revisit the time complexity of Heapsort. Best case, worst case, average case is all O nlogn. For the best case, there's a trivial case, which is when all of the keys are the same. So the best case is going to be on, which is very trivial, which really defeats the purpose of sort. If it's all equal, why do we sort anyways, right? So ignore that trivial case. All of the best, worst, and average cases is going to be O nlogn. Space complexity wise, it's going to be O1. Why is O1? Didn't we use a tree? No, actually the binary tree or the max heap is just a visual representation to help us understand. If you look at our code, you can see that we only used indices to manipulate on the array. We never initialized any extra temporary data structure to help us do the sorting work, right? Alright, heap data structure is a very powerful data structure. By itself, it's not only very practical in helping us implementing Heapsort, it has a lot of very practical applications. For example, priority queue is backed by heaps. So there are two types of priority queues. One is max priority queue, which is backed by max-heap. In real world, how do you schedule different jobs on the shared computer based on priority, right? So the ones with the highest priority is going to be scheduled and executed first, and then the next highest priority, then the third highest priority, right? The second priority queue is minimum priority queue, which is of course backed by minimum heap. A real-world application could be an event-driven simulator. So all of the items in the queue are events to be simulated. Each of these events is associated with a time of occurrence that serves as its key, for example. The events must be simulated in the order of their time of occurrence, because the simulation of an event can cause other events to be simulated in the future. So minimum priority queue is a good data structure to help us implement that. These are just a few simple real-world applications. Again, this is the code. This is the actual Java code, which is working. I'll put a link to my GitHub to this code. I highly encourage you guys to check it out, play around with it to help you deeply understand it. So if you like this video and you find this video is really helpful to help you understand Heapsort, and this is a very cool data structure and algorithm, please do me a favor and gently tap the like button. That's going to help a lot with the YouTube algorithm. And also, don't forget to subscribe to my channel as we continue to go through a lot of interesting data structure and algorithm problems, and I have accumulated quite a few on my playlist, so feel free to check it out. I'll see you guys in just a few short seconds. And also, feel free to comment and share on this video with your friends, classmates, colleagues. If you have any questions or comments, just comment down below in the comment section. I really appreciate it. That's it for this video. I'll see you guys in the next one.